Can you hear me? Up? Hello?
Yes, sir. Yes, sir.
मेरी आवाज आ
Yes,
रही है?
sir.
एक्चुअली लाइट चली गई तो वाईफाई कट गया ना, तो मैंने हॉटस्पॉट से जोड़ा तो उसमें टाइम लग गया, लेकिन अब मुझे पता नहीं ये कहाँ तक चलेगा क्योंकि इसकी बैटरी कुछ गड़बड़ है लैपटॉप की।
Okay.
अब देखते हैं, वरना देखेंगे अगर लाइट आ गई उस दौरान तो अच्छा है। ओके, सो मैंने सोचा मैं इसको फिर से ही करता हूँ क्योंकि उसमें आधा ही रह गया था और हमारे पास थोड़ा सा हम सिलेबस में आगे हैं। सो गिवन t, which is a continuous linear operator from bxy, where x and y are Banach spaces, they're complete. Pehla part, t is a homeomorphism if and only if t star, the conjugate of t, is a homeomorphism. Second, t is an isometry if and only if t star is an isometry. हमने एक्चुअली कल किया था आधा, लेकिन एक लास्ट वाला जो कन्वर्स था, हालांकि वो इजी था, सबसे इजी हिस्सा, बट वो रह गया था। प्रूव फर्स्ट, और जैसे कि हमने किया था, सपोज t is a homeomorphism. Homeomorphism. Now we know that, you know how it is defined. T star is a map from y star to x star. That's a bounded linear operator also. If t is from x to y, t star at y star is defined as y star composition t. Now that's the definition of the conjugate of t. Now we know that t star is a continuous linear operator. Continuous linear operator. So to show that t star is 1, 1, we show that its kernel is the singleton 0. We show that t star is 1 to 1. Okay, say because अगर t अगर y star belong करता है t, sorry, kernel of t को, it would imply that t star at y star is equal to 0, which would imply that because it's a function, so it means t star y star at x is equal to 0 for all x belonging to x, which means that y star composition, that's the definition of the conjugate, which implies that y star of t of x is equal to 0, which implies that y star at y is equal to 0 for all y belonging to y, because t is a bijection. T is a homeomorphism, T is a bijection. The homeomorphism has to be a bijection, of course, which implies that y star is the 0 operator, which means kernel of t star is just a singleton 0. Of course, which implies t star is 1 because it's linear. So, ये हिस्सा तो easy था. Next, we used open mapping theorem. Now, to show that t star is onto, that is sufficient actually, because we are dealing with Banach spaces. T star is onto, let x star belong to x star, then for all x belonging to x, we have x star x can be written as, because t is bijection, I can write it as t inverse of t of x. But that would be x star t inverse of t of x. And now what we see is that t inverse is a map from y to x, and x star is a map from x to k. So if you take this composition, applying x star after t inverse means this map here, it is a bounded linear map from y to k. It means that it is a sort of y star. So I can think of it as y star at tx, but that would be t star at y star, and a t star at x star t inverse applied to x, right? For all x belonging to x, which implies that x star is equal to t star at x star t inverse, where x star t inverse belongs to y star, which implies that t star from y star to x star is an onto map. So therefore, by open mapping theorem, it's a bijection there. Therefore, by open mapping theorem, T star is a homeomorphism. Homeomorphism. और जो converse था वो easy था actually. Conversely, suppose that T star is a homeomorphism. Homeomorphism. Then we know that there exists, because it's linear again, C positive, such that the inverse continuous है, तो it means T inverse of the unit ball in the x star would be contained in C times by star. मतलब ये मैं कल discuss कर चुका हूँ, which is true if and only if it is the same thing as C inverse of bx star is contained in T inverse of T of by star for some y positive. So basically it only says that norm of x star times C inverse is less than equal to, मतलब इससे एक चीज imply होती है, मतलब this is equivalent to this statement, because T star is T inverse is continuous, therefore T star would be bounded below. So that's what we mean by this basically, right? Okay, nevertheless, now what we do is to show that, what do we have to show? To show that T is continuous. And therefore, for all x, then for all x, देखो trick क्या थी? Then for all x belonging to x, norm of Tx by Hahn-Banach theorem can be written as supremum over y star belonging to less than equal to 1, sorry. Oh, let me, okay. Norm of, rather mod of, it's a scalar, y star t of x. That is the definition of, that's Hahn-Banach theorem basically, which is equal to supremum y star belonging to d sub y star supremum of t star y star at x. But that is the definition of the conjugate. This is what we mean by that. Supremum hai, so this should be greater than equal to, supremum of x star belonging to bx star, because of this thing, because of star, C inverse of x star of x. मतलब यहाँ स्टार नहीं लिखेंगे, यहाँ स्टार बहुत है, 1 तो by 1. So हमें मिला norm of tx is greater than equal to, मैं फिर से लिखता हूँ, supremum x star belonging to bx star some positive number c into mod of x star at x, which is equal to supremum x star belonging to bx star c inverse of x cap of x star. Now that's the definition of cap. You have to, what we distinguish it? It is basically j of x under canonical mapping. So definition goes like this. So okay, we have done it many times. So that would be C inverse of norm. By definition, it is just norm of this thing. So which is equal to C inverse of norm of x, because jx, norm of jx is always equal to norm of x. So or norm of x cap. Okay, so it implies that tx जो है is greater than equal to some positive number times norm of x for all x belonging to x. So that is C inverse of norm of x is less than equal to t of x. Like t of x is a bounded linear operator, so that would be less than equal to some c prime norm of x for some c prime positive. So it implies that, it follows that t is 1 to 1. वो तुम चेक कर सकते हो. I leave that to you, that t is 1 to 1. वही ना कि कर्नल इसका 0 होगा, वो तुम खुद चेक कर सकते हो using this. Okay, once we are done, उसके बाद कुछ नहीं करना. Hence t inverse, if I restrict the map to the range of t going back to x, is a linear homeomorphism. Because it is, हमने 1 1 prove कर दिया, तो t inverse exists. Or by this left-hand inequality restricted to the range, then this would mean that t inverse is continuous. That means therefore it's homeomorphism. Finally, since x is a Banach space, x is a Banach space, therefore t of x is complete and hence closed in Y. Now we have done that. Now t star is 1 to 1 because it is, by our supposition, a homeomorphism. It implies that t of x is dense in Y. तो हमने किया था ये रिजल्ट, t star is 1 to 1 if and only if, जब ना वो जिसके 4 पार्ट्स थे उसमें एक पार्ट ही था. अब अगर ये डेंस है, means that tx closure is equal to y, but this is equal to t of x because t of x is a closed subspace of y. It's equal to its closure, which means that t is onto. Therefore, t is from x to y a linear homeomorphism. Linear तो है ही, homeomorphism लिख देते हैं. मतलब वो तो हमारा supposition है, वो हमने प्रूव नहीं किया. linear, t is supposed to be linear. Okay, that's done. इसका second part तुम home assignment करोगे, और अगर नहीं करोगे तो वैसे एक जगह वो रिपीट होगा शायद अगले वाले थ्योरम में, इसीलिए मैं होम असाइनमेंट रखता हूँ. अगर कुछ बच्चे करेंगे तो अच्छी बात है, लेकिन अगर तुम नहीं भी करोगे तो शायद मुझे लगता है भानाक स्टोन थ्योरम में वो रिपीट हो जाएगा. एनीवेज, और वहां पे वो ज्यादा रेलेवेंट है. सो दैट वाज अवर. अब हम एक लंबा चौड़ा थ्योरम करने वाले हैं. थ्योरम एक्चुअली कंसिस्ट्स ऑफ 4 लेमास. उसके बाद हम, मतलब प्रूफ तो फिर उसका स्टैंडर्ड है. So what we do, before doing them that theorem, we define Cantor set. Cantor set में किया होगा, है ना? इसकी एक होम्योमॉर्फिक इमेज हम खड़ी करेंगे, यानी ऐसा स्पेस which is same as Cantor set, right? तो हम इसको डिफाइन करेंगे, जो हमने पढ़ा है ना, वो रिमूविंग द मिडिल थर्ड्स ऑफ एन ओपन इंटरवल देन टेकिंग द इंटरसेक्शन ऑफ ऑल दोस सेट्स, वो भी एक डेफिनेशन है कैंटर सेट की, बट कैंटर सेट कैन आल्सो बी डिफाइंड एज द कैंटर सेट, let us denote it by something, is the countable product delta equal to, अगर मैं लेता हूँ this set and take its countable product, actually where this 2-point set has the discrete topology, where 0, 1 has the discrete topology, मैं ऐसे इसको डिफाइन करूंगा, फिर मैं दिखाऊंगा वो जो तुमने पहले पढ़ा है, it's homeomorphic to this, as topological space it is the same. तो discrete topology हम लेंगे, that is हमारे कहने का मतलब है delta is the collection of sequences of this type x1, x2, so on and so forth, where xi is either 0 or 1. So actually we can replace 0, 1 by any 2-point set, koi fark nahi padta, it would still be the same topological space. Then DAP equal to summation n runs from, I should xy लिखूं कि a भी लिखूं? अच्छा, पहली बात तो ये है कि इट इज, देखो ये टोपोलॉजिकल स्पेस है तो इनका प्रोडक्ट भी टोपोलॉजिकल स्पेस है, so this is indeed a topological space, so this is a topological space, and of course 0, 1 is compact under under discrete topology. Discrete topology में of course this is a cover, is an open cover of 0, 1, because these are open sets in discrete topology, so therefore every cover can be reduced to, इसमें open sets है ही कितने, 1, 2, 3, 4, अब 4, any cover can be, every cover is a finite cover and it can be reduced to a finite subcover. Anyway, since actually any finite set in discrete topology would be compact, so this is a compact space under discrete topology, and by Tikhonov's theorem, since arbitrary product of compact space is compact, therefore this is also a compact space, compact topological space when I consider 0, 1 under discrete topology. Now we can also define a metric. Now dxy equal to summation n runs from 1 to infinity. I've got an minus bn अगर मैं लूं, divided by 3 raised to power n, where a is equal to a1, a2, so on and so forth, b is equal to b1, b2, so on and so forth, they belong to my delta. So defines a metric on it. Defines a metric on delta that generates the product topology, and it is generated, it generates, मतलब इसके जो open sets होंगे वो सारे के सारे open sets होंगे, मतलब product open sets होंगे. तो मैं उसको जरा क्लियर कर दूंगा, generates the product topology on delta. वैसे तुम देख लो, product topology को तुम ठीक से पढ़ो, रिवाइज करो उसको topology में से. Also, जैसा कि मैंने कहा था, by Tikhonov's theorem, delta is compact, hence delta is a compact metric space, क्योंकि it has got a metric that generates the topology, and that topology is compact. compact metric space. Now this is obviously a metric, right? Because a and b's would be either both zeros, या तो एक 1 होगा दूसरा 1 होगा. So you would have, but this has to be convergent. In case both are 0 तो वो term तो count ही नहीं करेगी. In case both are 1 वो term भी count नहीं करेगी. अगर एक 1 है दूसरा 0 है, so you will get something like 1/3 or 1/3 square. और अगर और क्या हो सकता है, या तो 0 होगा या फिर ये 1/3 1/3 and square. So actually this dxy जो है, it would be always less than equal to summation n runs from 1. ठीक है ना? So which is of course क्या बोलते हैं, geometric series of common ratio less than 1. So this is finite. So there is no issue with the finiteness. Then of course once that is done, this does indeed satisfy all the properties of the metric that you can easily check. सिर्फ इसको convergence होनी चाहिए. और अब ये कि ये generate करता है product topology. So ये मैं चाहता हूँ तुम सच में revise product topology, क्योंकि अगर मैं उसमें चला गया तो फिर हमें तो बहुत काम है. प्रोडक्ट टोपोलॉजी को रिवाइज करो एंड ट्राई टू शो दैट इसकी जो ये टोपोलॉजी जो है, जो कॉम्पैक्ट है, इट इज गिवन बाय दिस मेट्रिक. मतलब जो ओपन सेट यहाँ होगा वो उधर होगा और जो वहां होगा वो इधर होगा. गिव इट अ ट्राई एंड यू हैव टू रिमेंबर वहां के ओपन सेट्स क्या होंगे. देखो यू हैव टू टेक 0, एक तो होगा 0, या तो होगा 0 क्रॉस 1 क्रॉस सो ऑन एंड सो फोर्थ, फिर होगा डेल्टा क्रॉस काउंटेबल है ना. तो इसी तरह से मतलब you can have only finitely many non-deltas here. So that would be a typical basis set, typical open set in delta. और मैं ऐसे हिंट दे रहा हूँ ना, तुम कैसे उसको प्रूव कर सकते हो. तुम्हें दिखाना है that would be an open set and this metric वो easy होगा. इसी तरह से ज्यादा मुश्किल नहीं है, तुम कर सकते हो. Give it a try. Okay, once we are there, so we can also define Cantor set in this manner. So we call that C. Now let C0 be the interval 0, 1 and I remove the, and C1 I take to be 1, 3, 1. नहीं, मैंने क्या किया, गलत किया obviously. Middle open 1/3 जब हम remove करते हैं तो you will get 0, 1/3 union 2/3 1. And then you would have C3 को अगर मैं नाम दूँ और फिर 0, 1/9 2/9 3/9 खत्म, union 1/9 2/9 खत्म. So you should have 3/9 2/9 3/9 बचेगा. Union फिर होगा 2/3, that's 4/9. You should be 2/3 to 7/9 7/9 8/9 खत्म, union 8/9 1. इस तरह से अगर हम करते जाएं, so on and so forth, and let C be equal to intersection n runs from 1 to infinity Cn, right, as a subset of real numbers. और ये तुमने definitely किया होगा. Then C actually under ternary expansion can be written like this. It is actually equal to it's a compact set again, right? Yes, because it's intersection of, मतलब क्या कहते हैं इसको, it's a compact set. वो प्रूव करना पड़ेगा actually. तुमने किया होगा. कैंटर सेट में तो बहुत कुछ मटेरियल है, तुम बहुत सारी इसकी प्रॉपर्टीज कर सकते हो. एक ये है कि इसके टर्नरी एक्सपेंशन में जब तुम इसको लिखोगे, यानी इन दिस फॉर्म n runs from 1 to infinity an 3 divided 3 raised power n, then an can be either 0 or 2. 1 कभी नहीं होगा. So that's an important property of Cantor set. टर्नरी एक्सपेंशन का मतलब जैसे हम डेसिमल एक्सपेंशन लिखते हैं. I hope. अच्छा, चलो पहले मैं दिखाता हूँ ये होम्योमॉर्फिक है। नाउ देन सी थ्योरम एक करते हैं। हमने कैंटर सेट जिसका नाम दिया, तो कैंटर सेट डेल्टा इज, ये इजी है एक्चुअली वंस वी नो द टर्नरी एक्सपेंशन वाली प्रॉपर्टी, होम्योमॉर्फिक टू सी। एंड सी पे तुम्हें समझना है, इट इज जस्ट क्या बोलते हैं, मेट्रिक स्पेस, इट्स अ सब स्पेस ऑफ आर। सी इज सब, इसका आर के साथ कुछ कनेक्शन नहीं होता, we just created it, it is the countable product of the 0-1 interval. So delta जो अपना है, तो C is a subset, a subspace of real numbers which is a metric space under modulus, so it has this modulus norm या modulus metric. तो proof हम वही करेंगे, हम define करेंगे a function phi from delta to C by phi of a1 comma a2 so on and so forth. I put a sequence here where these are either zeros or ones, is equal to, हम define करेंगे summation n runs from 1 to infinity twice an divided by 3 raised to power n. Now as you can see, I get an element for each an. This an is either 1 or 0, which means that this numerator is either 2 or 0, never 1, because an is either 1 or 0, because of course delta mein hai na, delta is the countable product of this two element set 0 1. So of course phi is well defined, then actually it's a bijection, then phi is a bijection because the elements of C are precisely these types of elements, and it would be 1 to 1 because corresponding to every sequence of zeros and ones you will find that, you know, in the you will get these all possible ternary expansions which contain 2 or 0 but never 1, so that actually spans C, that's the whole of C. मुझे यहाँ ये नहीं लिखना चाहिए, कॉम्प्लेक्स नंबर के लिए सिंबल आदत हो गई है, this is just C kind of set. So phi is a bijection and also phi is continuous. Now phi is continuous, I again want to leave it to you. Just look at the matrix, right? And if for every epsilon there is a delta, both में use कर रहा होगा, यहाँ का metric, यहाँ का metric. Just take delta equal, चलो मैं लिख ही देता हूँ, take delta equal to epsilon by 2. In the definition of continuity, then phi is continuous. Now phi is a continuous bijection from a compact, ये भी तुमने topology में किया होगा, from a compact space to a Hausdorff space, because C is a part of R is Hausdorff, so C is Hausdorff, to a Hausdorff space implies that then P must be a homeomorphic. ये उतना मुश्किल नहीं है, उसकी वजह है कि Hausdorff space में closed set compact होता है, मतलब ये 3 लाइन का प्रूफ है कि if you have a continuous bijection from a compact space X to Hausdorff space Y, then its inverse would also be continuous. You just take the closed set. तो इसकी चलो मैं यहाँ लिख देता हूँ. If you have phi inverse from Y to X, right? Then X is compact and Y is Hausdorff. तो मैं दिखाना ये continuous. So it would be continuous. Why? If you take a closed set here, closed set अगर तुम लोगे, I hope yes, right. Closed set is a compact. In closed set is compact. Closed set is compact in a compact space. So this is compact. और इसकी जो image अगर under a continuous map, that means इसकी जो inverse image यहाँ पे होगी, phi inverse of this closed set F would be compact. and compact subset of a Hausdorff space is closed to phi inverse of f is closed. Oh, मैंने गलत किया. It should be phi inverse of inverse, right? So वो यहाँ पे closed होगा तो inverse image of every closed. मतलब ज़्यादा कुछ है नहीं. Anyway, तुम्हें सिर्फ मैं चाहूँगा तुम इसको continuous दिखा दो. वैसे उतना मुश्किल है नहीं. Just use the matrix on both sides. और मैंने कहा एप्सिलॉन को डेल्टा को ले लो एप्सिलॉन by 2 you're done. Because चलो उतना तुम कर सकते हो. Okay, now we come to the theorem जो हमें actually करना है. हमें करना है. Let me state the theorem. ये है every compact metric space is a continuous image of the Cantor set. Cantor set को हम लेंगे ये वाली शक्ल इसकी, क्योंकि हमें पता है it's homeomorphic to the जो तुमने पढ़ा है. So what we are trying to say, we can define a continuous map f from delta to x, where x is any compact metric space. और कभी-कभी तुमने यहाँ देखा होगा, it is the same thing as compact metric or metrizable है, जिसपे हम matrix define कर सकते हैं. कुछ books metrizable लिखते हैं. So every metrizable space is a metric space. Actually कभी-कभी हम ab initio metric define करते हैं, कभी-कभी it's indirectly. मतलब हमारे पास कोई और चीज है जिसकी मदद से हम metric define कर सकते हैं. मतलब we are given a topological space and under certain conditions we can define a metric on it. We call it a metrizable space because it was not ab initio a metric space, although that's not relevant that much here. तो लेकिन कुछ books लिखते हैं metric की जगह metrizable space, but it would nevertheless apply. So it's a continuous image, so you can define a map onto map from delta to x for any compact metric space x. हाँ, तो in case तुम सोए नहीं हो तो I want to, अभी तक कोई तुम्हें कहीं पे समझ नहीं आ रहा है कुछ, तो तुम्हें वो मैंने बोला टोपोलॉजी का थोड़ा रिवाइज करना है, स्पेशली द प्रोडक्ट टोपोलॉजी. और ये चूंकि खत्म होने वाला है मैं इसको उसी में लिखूंगा. और दूसरी बात ये कि मैं कह रहा था वो यू नो दैट बाइनरी टर्नरी एक्सपेंशन जो हमने अभी कहा, ये किया है ना तुमने? आर यू लिसनिंग? हैव यू डन दैट ternary expansion of the Cantor set can have only 0 and 1, 0 and 2, never 1. उसको प्रूव किया है तूने कभी?
No sir.
कभी नहीं?
No sir.
टोपोलॉजी में भी नहीं, कहीं
No,
पर भी नहीं. तो उसको तुम, मैं थोड़ा टर्नरी एक्सपेंशन के बारे में बता दूंगा, बट आई थिंक कैंटर सेट पे बहुत ज्यादा वो होगा मटेरियल ऑनलाइन, तो वो तुम चेक कर सकते हो. सो बट क्या बोलते हैं, वो करना जरूरी है. बट आई विल टेल यू अबाउट एक्सपेंशन, उससे तुम्हें आइडिया आ जाएगा कि कैंटर सेट में क्यों ऐसा होगा, वन नहीं होगा उसकी टर्नरी एक्सपेंशन. लेट मी स्टॉप इट, लेट यू रिजॉइन. मैं अभी शुरू करता हूँ. अभी तक हमारी बैटरी चल